Okay, the next talk will be held by James Forshaw. He's a security researcher at Google's Project Zero with over 10 years of experience from web browsers to VMs. And talk title is The Joy of Sandbox Mitigations. It's about more or less not so much known Microsoft mitigating controls when creating code. So I'm quite interested to see it. Thank you.
Good afternoon, troopers. Okay, so yeah, I've pretty much been introduced already. I don't think I need to go too much further on that. One thing I will say is I do work and help out the Chrome team on Windows to try and improve the sandbox security on that platform. So I'm sort of coming from that sort of angle when I'm going to be talking about the stuff here today. Now, I'm specifically talking about things Microsoft have introduced to Windows to make application sandboxes more secure, so sort of user mode sandboxes. And we're thinking about this more in the sort of concept of security boundaries as opposed to like a sandbox which you say run malware in to see what it's doing. Now, there'll be hopefully some bugs, some interesting edge conditions, and also sort of information about how it's actually implemented in Windows itself under the hood. And the research was primarily on Windows 8.1 and Windows 10. That's actually mainly because these are the only platforms with a substantial number of these mitigations implemented. So before I start, there is a big warning that there will be lots of code snippets as we go through. If you're not happy with that, then unfortunately, too late now. But I am sorry for that. I do really try and apologize. So let's get on with it. Now, I'm sure even if I asked for hands of who didn't know what DEP was or no execute protection, there probably wouldn't get many people admitting to that. But DEP was pretty much Microsoft's first attempt at like a process level mitigation to try and prevent or make exploitation more difficult. And it's kind of a part of a class of similar mitigation strategies, things like ASLR. ASLR, Adjust-Based Layout Randomization, is there to try and make DEP more useful. And it was introduced in Vista, basically making it so you couldn't predict where executable code was in the process. There's other stuff like Safe SEH, Stack Cookies, Control Flow Guard, which is a fairly modern introduction. But all of these are basically there to stop a bad guy compromising your application through a document or a web page. And it's kind of like the first stop in the door. Like you're trying to prevent them even getting through the front door in the first place. But of course, like if you take lessons from sort of network security, especially with the wonderfully banded around terms of APT, etc., you kind of got to assume that you are already compromised, that someone can get in that front door and potentially run code inside your process, your browser, your document reader, and actually then do something interesting with that. So of course, pretty much any sort of untrusted facing application of any significance now implements these sandboxes to try and almost like take it that it's given that someone will already get RCE. Someone will already have compromised that process, and we just don't want them to kind of progress further from that process and compromise the entire system. And that's the sort of the general theory behind it. So this is what sandbox mitigations are all about. They are basically trying to make that sandbox on the Windows platform more robust, make it more difficult for the attacker to go from RCE into full system compromise. Now there's three sort of strategies which mitigations usually sort of fill in when they're trying to actually implement their goals. And the first main one is actually reducing attack surface. So this is, you don't want, the less code an attacker can get to, the less code they can attack, and the less code which can be compromised. Because all code has bugs, unfortunately. Yeah, it would be nice if there was a technical mitigation against bad coders, but unfortunately that doesn't exist. So yeah, reducing attack surface is a big goal. But then there's sort of more soft goals. These are sort of goals which don't play necessarily on the technical aspects of the sandbox, and instead play on the sort of the mentality of the attacker. If you've got an attacker, say a criminal organization, they want to compromise machines because they want to stick their ransomware on. Well, the whole reason of doing that is they want to extract some monetary value out of you. Now, if the cost of exploiting individual machines is more than they're going to get back in ransom, well, it's kind of like their return on investment's it's not worth the effort. So if you can increase the exploit cost sufficiently by some sort of technical control, maybe that would be useful. And a counterpart to that is reliability. If you can make it so whenever someone tries to escape a sandbox, they have a 1 in 10 chance of it succeeding, well, again, that has basically dropped their return on investment down to 10% of what it could have been. And so effectively, it hurts their bottom line and hopefully makes it, while not impossible, less likely to be attacked if you're actually employing these strategies. Now, of course, you can kind of see this in the sort of world of web browsers. Chrome, like you'll see a Flash 0-day appear, and even though Chrome actually ships with Flash and only sort of Internet Explorer and Edge have it as well, invariably, Flash exploits go against, say, IE or Edge as opposed to Chrome, because you end up in a much more strong sandbox, and the value of a sandbox escape in Chrome is usually higher than it is out of IE. Okay. So I've categorized the mitigations I'm going to talk about into two sort of main groups. Firstly is explicit mitigations. These are things you actively have to modify your program to sort of use, or at least actively enable. These can be things like, obviously, making it into a sandbox in the first place, modifying the way the process access checks work so that it actually works in a sandbox environment. But also things which I'll go into, which just basically even make the code itself maybe less reliable, so you need to modify things to actually get it to work, or just general features which are not something they can turn on by default on a general application. The second category is implicit mitigations, and these are things which Microsoft have now added to Windows, which as long as your process is running within the context of a sandbox, so whatever Microsoft defines as a sandbox, it will actually enable these by default, and there's actually no way of turning these off. Now, this is rationalized based on the fact that it probably isn't a breaking change. Some of these features are not stuff which sandbox applications should have ever been using in the first place. But they're just useful ways of then reducing attack surface, reducing exploit chains so that it's harder to attack a sandbox. Okay. So I'm going to go through sort of each one in turn, and this is sort of where the code starts appearing, I'm afraid. We'll start with explicit mitigations. So introduced in Windows 8 was a new API call, Set Process Mitigation Policy. And it kind of does what it says on the tin, in that you can specify certain classes of mitigation policy and apply them to your process. So you've obviously got your policy type, the accompanying data which represents what is actually being used. Now there's actually sort of 11 defined. If you go and look in the Windows 10 Threshold 2 SDK, there's currently sort of 11 policies defined. And actually, a good half of those we don't really care about. Either they're invalid, or they're things like DEP and ASLR. We're not going to talk about sort of DEP and ASLR stuff, because that is, as I say, more of a front door mitigation rather than a sandbox mitigation. But that still leaves us with sort of 5 different mitigations we can talk about. Only 3 of them are on Windows 8.1. The other 2 are Windows 10 exclusive. And the process signature policy, as you can see, is yellow. That's actually because while it is available on Windows 8, it doesn't actually work through the set process mitigation policy function. And that's because the user code which implements this, the set process mitigation policy function, has not been updated to match what the kernel is actually able to support. And this is actually how you set it manually. In this case, it's using the system call ntSetInformationProcess with a particular type, and you can specify this signature mitigation policy on Windows 8.1. And all of them basically use the same functionality. So if you wanted to actually look at the implementation of how it sets the bits, this is where you go and look in the kernel. A slight odd quirk is, even though that function takes a process handle, so you can specify an arbitrary process handle, it will actually fail if you specify anything other than the current process. So you can't apply these mitigation policies directly to an existing running process, which is a bit of a shame, in my opinion. But fortunately, you can set mitigation policies when you create new processes. Some policies are sort of, you end up potentially with a race condition that if you don't turn them on immediately, they may get attacked before you have the chance to turn them on. And things like ASLR and DEP kind of have to be turned on sort of by the time the process is even up and running. So there is actually a way of specifying what mitigation policies your new process wants to have. And this is using these special process thread attribute lists, which are just massively confusing, but that sort of sample code is basically all you would need to set a mitigation policy. Now, if you have an application you would like to try and apply these mitigation policies to, but you don't want to write a launcher, and obviously the code itself doesn't support these mitigation policies itself, you can actually use also something called the image file execution options. You may have encountered this if, for example, you wanted to attach a debugger automatically to a process, and you specify the executable name, so in the registry, and then you can specify this mitigation policy value, which is a 64-bit word, which contains these bit fields, and then the same bit fields as you would use at process creation time. Now, one thing which, as far as I'm aware, isn't documented, if you've ever used image file execution options before, you'll know that effectively it always matches just on the executable name. So let's say, for example, you want to apply these mitigations to notepad.exe. By default, every file which is called notepad.exe, even if that is not the notepad.exe you expected, would have these policies applied. And okay, not many things should be called notepad.exe, not notepad.exe, but it's still kind of annoying. For example, like if you had multiple copies of the same program, say a beta and a stable version, and you couldn't actually apply mitigation policies to one versus the other. So this undocumented feature allows you to apply a filter, which is based entirely on the full path name. And so you can specify sort of the name as usual, put use filter on, and then you can put an extra key underneath it, and then specify the full path filter. And that's where you can put your mitigation options. And so you can actually apply this like selectively to very specific processes. So let's have just a little quick demo. I hope everyone can see that. Should be able to. I think it's big enough. So I've actually set my notepad filter, and I've set it to C Windows Notepad. And strangely enough, Windows actually, Notepad is under Windows for legacy reasons, because that's how like Windows 95 placed it. But actually, there's also a copy under System 32. So if we run the two different versions, we can see that we'll get different mitigations. So Windows Notepad, so one copy, so and I do system32.txt, just so we know that it's a different thing. Okay. And I've got a tool, oops, sorry. So I've written a suite of tools to do sandbox analysis. You can download them off GitHub. I'll give you the link at the end. But one of the tools is dump process mitigations. And this actually will dump those set process mitigation policies for you. So we do that with Notepad. And we can see that we've got one copy of Notepad, obviously with a few extra mitigations as to the other one. And that obviously makes some sense. And we can obviously run up things like, for example, Chrome, which has its own set of mitigations. So if we change that to Chrome, we can see obviously we've got all manner of extra ones on that one. And obviously same with Edge and things like that if we actually applied that. So now it's time to actually go through those 5 policies, how they actually are implemented, how you would actually set them. And the first one is dynamic code policy. And effectively, this is essentially just stops a process from creating new executable memory. or changing existing executable memory so that you could try and mitigate against an attacker's shellcode. So say, for example, an attacker has obviously gained RTs. He can gain control over the instruction pointer. He then runs, say, a ROP chain, and maybe he then copies some virtual allocs, some executable memory, copies a buffer into it, and then runs like proper shellcode. So it's nice and reliable because it's just a simple piece of code. This kind of policy is there to try and make it so an attacker, if they didn't realize that that was going on, would fail, or actually, if they know it's going on, the best that they can hope for is trying to do everything in a ROP chain, which obviously is possible. It's just a bit more annoying and a bit more costly and less reliable. So it pretty much disables all the known suspects. Virtual alloc, map view of file as an executable image, virtual protect, changing the protection of an existing block of memory into executable code, and even things like reconfiguring control flow guard so that you can't set new process targets, executable targets. But it doesn't do anything against loading DLL. So a wise attacker could obviously come along, and instead of doing their ROP chain, they just ROP to load library and, say, load a DLL from a web dev share or a local file that they managed to drop. So it's kind of useful, but it doesn't solve all your problems. And obviously, a lot of the big targets of these sort of mitigations, things like web browsers, they kind of already need to do things like JIT. And JIT, if you do that, you've got a problem. Like, if you can't create executable code, you're going to have a very slow JavaScript engine. Now, under the hood, there's a function which basically just looks for a flag in the eProcess structure. The eProcess structure is the kernel object which represents a process in Windows. And there's just a flag in there which says, is dynamic code blocked? Now, as the text below it states, you might assume that the process you're passing to this function would be the process with the mitigation on, like the process you're trying to insert executable code to. But it turns out it's not. It is actually the caller. And there's certain functions, such as virtual alloc ex, which takes a process handle, and you can inject executable code into another process. And it turns out that is not actually mitigated against. So obviously, if you're only ending up in a sandbox environment, you've got this mitigation policy on. But you could actually write it in such a way that, say, your JIT runs out of process and injects that executable code into your sandbox. I think this is actually how the iOS executable JIT works for Safari, because they can't allow Safari to create executable code. That would be a problem. So they actually have a secondary process with a new entitlement which allows it to inject executable code. Now, in order to mitigate against an attacker trying to just load a library, there's also a few other policies. So the first one, binary signature policy, basically states, it gives sort of a very simple binary value of what code signing is supported for images you load into your process. So originally in Windows 8.1, there was the Microsoft signed. So anything signed by Microsoft was allowed, but anything unsigned or signed by some other authority was not allowed to be loaded into your process. In Windows 10, they've introduced store signing. So store signed is where if you download from the Windows Store, it's not strictly Microsoft signed. It's signed by like a cross sign of the Microsoft cert. Now, if you want to create this, if you want to use this from create process, you can actually only specify Microsoft binaries. For some reason, they didn't introduce the store signed. It's possibly because, as you'll probably see later, that they ran out of bits. They ran out of 64 bits to actually implement these mitigations. Obviously not thinking ahead. So under the hood, again, it's pretty similar. In this case, rather than just entirely relying on certain flags, it uses something called the process signature level. And this has actually been implemented for things like protected processes. So you can have a protected process which has a certain signature level, and it stops people accessing that process. But it can also be used for just specifying what parts of code integrity actually verify what signatures are used. Now again, interestingly, the check is not done on the process with the mitigation. It's actually done on the caller. So again, you can create a process and map arbitrary image sections in. But curiously as well, even though you can specify this mitigation at startup, the main executable file is not verified under this policy. So you can create an arbitrary executable, any you like, signed with anything or unsigned, and subsequently, no other image can be loaded into that process which is not Microsoft signed. And that's kind of useful because it makes it harder for people to inject DLLs. If they inject a thread into the process and try and do call load library, it will fail. Now, the next thing which is introduced in Windows 10 only is kind of just an extension of that. It basically prevents you from mapping either images coming off a UNC share or images which have what's called a low mandatory integrity label. And the low label is basically applied, if you're running in a sandbox and you write a file to disk, it's probably going to end up with this low integrity label. And actually, therefore, you can't easily bootstrap a DLL from temporary internet files because it will have a low label. That's the theory behind it. And again, pretty similar implementation. Has some flags, calls this particular function whenever it's trying to map an image. And if it's either a remote file or it's a low integrity file and that policy is turned on, it won't allow you to do anything. OK. So that's sort of more, I suppose, making the attacker work harder for their money. They're trying to stop either trivial ways of getting shellcode to work or loading libraries into the process. These last two policies are actually more about, they're more about attack surface reduction. So I'm sure if you know anything about sort of Windows kernel exploitation, font vulnerabilities are pretty much a goldmine for kernel exploits because they're almost always accessible from pretty much any sandbox. The code is written by Adobe, which obviously is a bad thing. That's a bit unfair. But it's very complicated. Like TrueType fonts, for example, have their own little bytecode engine which it runs just to render a glyph. So all these things lead up to basically massively complicated problems. So Windows 10 actually tried to mitigate against this in two ways. Firstly, they introduced something called the user mode font driver. And now any sort of untrusted fonts, instead of running in kernel mode, should be pushed down into user mode. So even if you were to find a font vulnerability, it wouldn't just gain you kernel execution. Now, the second one they added, and I'm assuming they added this because they had two completely different teams working on the same problem, was the font disable policy. And instead, what this does, it's a mitigation policy which says, are you allowed to load custom fonts at all? If not, then we just reject them. And a custom font is either one which comes from loaded from non-system font directory, so Windows fonts, or it comes from a memory structure. So you can load a font from memory itself. Now you can turn on auditing, so you'll get an event log if someone tries to load a TrueType font or whatever, and it will give you sort of rough indication of which process was doing it and also where it was. So you can actually you could potentially bring these back. If you ever use this in an enterprise environment, in theory, you could bring it back and see if anyone is tripping up on the policy. And Emmet 5.5 actually introduces a feature which allows you to turn this on for arbitrary processes. And it uses the same thing under the hood, effectively. So yeah, it can be used, and while it's not sort of the greatest mitigation, it's certainly reducing attack surface which you would rather not expose to sandboxes. Now, under the hood, this is all implemented in the Win32k driver, which is not part of the kernel. And technically speaking, even though it's set in a flag on the eProcessor structure, Win32k isn't supposed to know the structure of the actual implementation of the eProcessor structure. So actually, it has to call the query information process function to retrieve the actual policy information for that font system. And then it just does a check. It basically opens a file here and then says, is this file, it basically extracts its name, is this file in the system font directory? If it is, if it isn't, and the policy's on, bail, log it, or actually completely bail. And then finally, it will actually open the file itself. Now, I don't know whether anyone can spot the bus-shaped hole here, from a security perspective, of opening a file here, then opening a file here. So, okay. So I've written a really simple application which will just try and load a custom font off disk and display it to the user. So at the moment we can look at our event log and we've got no logs. So it's completely empty. So if we run, oops, I'm sure I turned that off, but obviously not. Anyway, run, no, exploit. Right, so this will run it, and I'm not going to try and do the exploit at this point. And it obviously tells me, nope, sorry, you can't load that. We get boring Arial as our font. It's terrible. And we obviously get our event logs, which says, this process has tried to load this font off disk. So, let's see if we can exploit it. Oops. So, in this case, you could do it all in the same process, and I have an implementation which does do that. But just for demonstration purposes, just to show how it's actually working under the hood, I'm actually using a tool which comes with my symbolic link tools, which I sort of released for presentations last year, called bait and switch. And bait and switch, basically, it creates a symbolic link to a file name. It waits until someone opens that file. So in this case, it's opening it to verify that it's in the system font directory. So we initially pointed at a system font. And the minute we see that occurring, we switch the symlink so that the file link now points to somewhere completely different. So by doing this, in theory, I'm crossing fingers it works, it should actually bypass our check and then load the untrusted font. Okay. So we should see, yeah, just sort of basic information. It's switched the symlink for us underneath the hood. And yeah, I haven't actually told Microsoft about that one because it kind of is, oops. It kind of, because of other mitigations I'll go into, it actually doesn't sort of gain you much in a sandbox. And actually, the mitigation policy, if you're outside of a sandbox, say you're just running a normal application, well, actually, the way the user mode font driver works, you'll only exploit a process with lower privileges than the process in which you're already in. So actually, it looks cool, but it's actually not quite as useful as it looks, unfortunately. But anyway. Next one, or the final one, is the system call mitigation policy. So this is kind of like the ultra way of stopping font attacks, because basically it just kills the entire UI part of the kernel. So the Windows kernel actually has two sets of system calls. It has normal NT system calls, and it has the system calls for the windowing system, Win32k system calls. And this syscall disable policy basically blocks access to all Win32k system calls. Now, you might think, OK, maybe the implementation should be obvious. OK, we set a flag. If we're trying to call a Win32k system call, block it. Yeah, easy, easy. It's not how it's actually implemented, unfortunately. Instead, it goes, is it a Win32k system call? Cool, OK. Is it actually, is the number greater than the current length of our system call table? Well, OK. Let's assume that it's not. Right, OK, we need to convert this thread to a GUI thread, for whatever that means. And that basically sets the current thread's system call table, which then means that it will now be longer and will actually execute it properly. So you can see from this, there is no check of that flag. So where is the check coming? Well, the check is here. So the check is in this PS convert to GUI thread. And what actually this means is that the mitigation, if you don't apply it and then somehow invoke Win32k system calls, the thread becomes converted to a GUI thread, and is actually, it can't be unstuck. It can't be un-GUI threaded. So even if you then apply the mitigation at a later point, it will actually not help you. In theory, there'll be a thread running around which has access to Win32k. So yeah, you'd think, OK, I'll write my process so that it never calls anything in user32 or GDI32. Unfortunately, like, so many libraries rely on the facilities of user32. Say, for example, you want to use COM. COM can, if it's using single-threaded departments, use a window to actually post messages between objects. Horribly inefficient, but that's what it does. So obviously, COM relies on user32, which relies on GDI32, which then invokes Win32k calls, which makes your initial thread Win32k enabled. So if you try and late bind, and by accident you somehow either directly or indirectly link Win32k code, it's going to be a GUI thread, and your mitigation is basically useless. So okay, you might think, let's apply it at process startup. Yeah. So you can turn it on after, and it will actually tell you, sorry, you were too late, but it will already set the mitigation for you, so kind of silly. So if you do it at process creation, it should work, hopefully. Well, actually, it gets even worse, because basically what happens is during the initialization process, if any DLL fails, it will cause the process to die. And usually die in some horrible, horrible way. You have no idea why. And ironically, it'll try and pop up a dialog box for you to say why it's failed, but obviously you've turned on the mitigation policy, so it can't show you a dialog box. And it effectively just sits there forever. Awesome. So you might wonder how on earth does something like Chrome do it, because Chrome uses this facility. Chrome has to be very, very tricky, and it hooks the system call, which maps an image into memory, maps a DLL into memory, and then effectively just modifies that DLL as it's coming into memory. Because if you let load library get its hands on it, it will already have invoked the loader function, which means that it's already broken. So it has to like hook the lowest possible level. And we can see here that there's a few other functions as well that it has to mitigate, otherwise something else blows up. And something else blowing up is because of a really weird bug in their implementation. So we look at these two calls. Create compatible DC. I'm not going to explain what this actually means unless you know much about Win32k programming. And get user DC. They both return this HDC, which is a handle to a device context. Now, in theory, both should return null on error. Now, what could be more of an error than there actually being no windowing system? You'd assume that that would be fundamental failure. But if you actually call these functions under the mitigation policy, yeah, get DC returns null. That seems to work. Create compatible DC returns this weird value, which seems to not really correlate with anything else. Huh, that's kind of odd. So it turns out that they've got some backup code. Basically, when PS convert to GUI thread fails, it has some backup code to say, OK, this function is supposed to return a status code, or it's supposed to return an integer, or it's supposed to return a handle. And most of the GDI calls I've found have the wrong flag set, because basically it sets the flag to 1, and that flag in this structure basically says return the status code. So get compatible DC is returning the status code, which just happens to be status invalid system service. And if anything then relies on that, it tries to call get compatible DC, and it works. It doesn't return null. That's not an error. You then pass that to some other function, and all of a sudden that process crashes because it assumed that like something had succeeded when it hadn't. Now, one of the strange, or I suppose intentional behaviors of these mitigations is once they're on, you can't turn them off. Like, if you could disable system Win32k, and then you could just turn it back on again, that wouldn't be very much of a mitigation. That would be pretty easy to exploit. So what they do is, like, pretty much when you set them, it says, is it already on? If yes, access denied. You're not turning it back off. But what happens when you create a new process? Does anything actually get inherited across that structure? And it turns out, actually only two do. System call disable and image load. And effectively, the system call disable is an obvious one. Like, you don't want to create new processes which can attack Win32k. But image load is probably because it stops an attacker, instead of calling load library, they call winexec with run DLL32 passing their DLL to it. And it's presumably just to mitigate against that. So, OK, we would ideally like our sandbox to never be able to spawn a process. And so things like Chrome use something called the job object. This has like an explicit, you can only ever have one active process in your job object. Okay, you're not allowed to break out of it. You don't have permissions to break out of it. But there's a real big problem with job objects. Namely that anything outside of a job object is fair game. So for example, WMI. WMI has a create process function. If you're in a job object and you have sufficient permissions to talk to WMI, you can just get it to create a new process. Doesn't matter what the job object is, doesn't care. Another bug I found actually is actually a bug which Microsoft has never actually fixed. It's by design. There is a system driver, kernel driver, which is responsible for creating the window which hosts your console. So when you create a new command prompt, it creates the executable which hosts that window. And this is really alloc console function. And intentionally, when it creates the process, and this is in kernel mode, it sets the flag which says, regardless of what job object you're in, I want to break out of it. And because it's in the kernel, even though it would normally require a privilege, so the user code can't call it directly, it actually escapes and creates this conhost.exe process. At which point, the user process can obviously go, hey, I'll just hook into that, and maybe spawn a new process or whatever it needs to do. So, after I pointed out this console driver one and expressed how sad I was with Microsoft for doing this and them not fixing it, they threw me a SOP and they sent me they introduced a new mitigation. Now this is completely sort of unrelated to how the other mitigations work, but effectively it allows you to stop processes being created. And the beauty is it works not only for WMI and console driver, so something cool must be going on. So it's actually an interesting implementation. What they've actually done, instead of doing it on the process, which would not work for things like WMI, instead it does it for the token. And the token is your access control mechanism. This is associated with every process. And this can be inherited across process boundaries to WMI via impersonation. So effectively, it mitigates both WMI and console driver and effectively makes a process token incapable of ever spawning a new process, which is kind of cool. And before I just finish on this bit, it's worth pointing out things like low-box tokens. Low-box tokens were introduced in Windows 8 for store support, and there's actually loads of like interesting sort of implicit mitigations which sort of appear, or explicit mitigations. You have to enable a low-box token, which allows you to sort of reduce attack surface and things like that, which is kind of cool. Okay, so that was explicit mitigations. Now I'm just going to quickly run through some of the implicit mitigations that Microsoft have added into the sandbox. Now, in Windows 8.1, Microsoft introduced a function called EXIS restricted caller. And what this function is used for is to try and mitigate against KSLR leaks of kernel information, ASLR information out of the kernel, which would then facilitate a sandbox to allow them to improve the reliability of their attacks against the kernel. So it does loads of different things, but it is just sort of like a way of bolstering up KSLR, so you're not leaking quite so much information to the outside world. Now it's worth, like Alex Ionescu's got quite a good blog on this. It's worth reading if you're interested about all the different things it actually mitigates against. I'm more interested in this function. So this function looks almost exactly the same. You can specify a sort of an explicit like token to verify, but all it's doing is saying, is this process running with a lower integrity level than normal? So it checks against medium, and if it's medium or above, it'll succeed. Now, while it's almost exactly the same, it's used for a completely sort of different reason, and this is used for actual implicit sandbox mitigations. So it was introduced in Windows 10. But interestingly, backported, I think actually all the way to Vista. I think that's actually wrong. I think they backported it all the way back, which is kind of cool. So this is things like the blocking of symbolic links. So I don't know if anyone saw my talk on abusing symbolic links at SciScan and Infiltrate last year. Basically, this is all the sort of things I brought up and kept beating on about, and Microsoft eventually cracked and decided to do something about it. obviously, it was easier to fix this in a sandbox than it was to fix all the myriad of bugs people were reporting, which use the same facility every single time. Same bug, different product. So yeah, object manager symbolic links are a funny one in that it doesn't stop you creating them. Like you'd assume, like a good mitigation is you can't even create something called a symbolic link. But in fact, it doesn't work that way. If you create a symbolic link in the sandbox, it marks that symbolic link with a special flag. Now, if an unsandbox process, so a more privileged process, tries to access that link, it checks the flag and refuses to honor that request and just returns object not found. So this is actually why that attack I showed on the custom font disable block doesn't work in a sandbox, because you can't create these sort of symbolic links anymore, or as easily, which actually would then be followed by this higher privileged kernel level facility, which is actually exploiting them. So yeah, this is the reason why, and this is why I didn't think it was worth reporting to Microsoft, but of course, maybe Microsoft have a different view of that. Hopefully not. Another symbolic link type, registry key symbolic links, they just went for the full-on ban. You just can't create them in sandboxes at all anymore. Literally, if you either try to create a link or you try and modify an existing link, it will ban you and say no access denied. And then NTFS mount points. Mount points or junctions or directory symlinks, depending on what you want to call them. Again, were a useful attack mechanism for breaking out sandboxes. If you could get a privileged process to write to a arbitrary directory, you might be able to redirect them to some other location on the file system. So they implemented a mitigation. But it turns out, apparently, and this is from discussions with someone in Microsoft, Silverlight used these in a sandbox. And so they couldn't block them entirely. They actually found that it was they tried and then found it was actually not something they could do. So instead, they thought, okay, let's implement a check. Is the target of this mount point a writable directory from that user? But as we've seen, just because you can open that file once in the current process doesn't mean that an unsandboxed process will even open the same file. And we can see that here. So yeah, if we can get our sandbox process, if we can set a mount point to a writable directory, but just happens that if you apply that path to a different process, an unsandboxed process, it actually hits a completely different path, then you've got a potential bypass of the mitigation. And eventually, hopefully, you say, hey, write me a file, and it will just write you to an arbitrary file. So the way this works, or the way my original attack worked, was exploiting the fact that while you can't, this is sort of like an NT path. So you've got this crazy-looking / question mark, which is the DOS device directory. You've got the derived letter, and then you've got the path. And this maps down to a per-user device directory. So this is created for individual users on the system. This allows you to have, say, the Z drive map to your share, and on a terminal server, someone else can log in and map the Z share to somewhere else entirely. Now, you can't actually write to that directly, which means that you can't change the symlink and you can't change the path. But I realized that there was a facility which you could use which changed the device map, the process device map, on a per process basis. So if you're running in the context of that process, it uses one device map, and if you then end up in this unsandboxed process, you have a different one. And because it's something I can control, I can modify, say, the C: drive to point to anywhere I like. So obviously, this points to a completely arbitrary location, which ends up as a writable directory. But crucially, when the unsandboxed process opens it, it actually just opens C:/Windows, because it has no idea that you're doing something crazy under the hood. So I told this to Microsoft, and they did what was probably the obvious approach. They didn't fix the check, because the check was too hard. The check was too difficult to fix. So they just fixed the sort of expression. This is like your traditional, there's a cross-site scripting in this parameter, and maybe some other parameters, and they fixed that one parameter, basically. Bloody annoying. But of course, it's a new mitigation they've added, new implicit mitigation. You can no longer use this trick in sandboxes. So by the time I saw the sort of patch, I already had my bypass exploit working, which instead used the facility of you can impersonate the anonymous user. And the anonymous user has a device map, which everyone can write to. And I just use that instead and just do it that way. And then there was another fun trick. You can look at the issue tracker, the Project Zero issue tracker for those issues if you want to have a read of how badly you would do it. They have now fixed the check, and as far as I can tell, that check is pretty robust. They're creating the file and verifying that the file is where it is and taking the path and actually using that path now as the actual file destination, et cetera, et cetera. So it seems a lot more robust than it was. And I haven't found a way to break it, but that's not to say there isn't a way. Now, of course, they took away all these symbolic links, and I was like, oh well, never mind. But I thought, okay, there's other fish in the sea. What about hard links? NTFS supports hard links on the same volume, and there was an interesting property I noticed. Even though this function, if you call it a create hard link API function, it requires write access to the linked to file. Turns out, actually, that wasn't necessary. And you could specify any file as long as you could open it for read access, and it would work. Just not using this, you'd have to implement your own. And this is kind of a demonstration of why you should never give a vendor your slides before a talk. Because I obviously said, hey, Microsoft, you want to check my slides out? Because there should be nothing contentious in them whatsoever. The slides actually contained like a demonstration of an unpatched sort of user-to-system elevation. I was expecting them to complain, oh, just please don't keep harking on about that. No, they said, hey, can you redact those slides and hard links for us? Huh, okay. We'll fix it. Like, we consider it now a mitigation, like bypass, effectively. It's considered to be a mechanism you can do sort of symlink-style attacks, but we've already tried to mitigate symlink-style attacks. So we'll fix it. Okay. Sure, why not? And being Project Zero, I go, and you have 90 days, and the clock is ticking. And if you don't get it fixed, I'll be sad, obviously. So yeah, now if you try and create a hard link, if you're in a sandbox, it will require that you have write access to the target file. Otherwise, it won't work. So yeah, that's pretty much the sort of the run of the mitigations that Microsoft have put in. If you were to want to try and implement these yourselves, the sort of ultimate set of options is obviously run it in a sandbox to begin with. If you're in a sandbox, those implicit mitigations kick in. The aspects of symbolic link mitigations, which, for example, Chrome and IE, etc., have all been attacked by before, and now effectively they are pretty much completely eradicated because a sandbox, barring any bypass, can't actually get into them. And if you can, turn on Win30k lockdown, block custom fonts, do all that sort of cool stuff. And yeah, it's worth a try. So just quickly wrapping up, Microsoft have improved quite a lot in this regard. They're now sort of treating sandbox escapes as actual sort of vulnerabilities. Previously, like for Internet Explorer protected mode, it was considered that basically protected mode was so rubbish that they were not going to support it as a security boundary. But now, actually, they're taking it on that Microsoft are implementing features which only work in security boundaries, and if you can bypass them, they will actually fix them, which is a bit of a change of Microsoft's thinking. And you can make a fairly secure sandbox, but it would be nice to have better facilities for things like syscall lockdown. Just having, I want all of Win32k or none of Win32k, as you saw, has massive implications for process creation and things like that. You have to do crazy stuff to work around that fact, which is quite annoying when you're developing these things. But it's still good. Hopefully, Microsoft are going to add more stuff. I've not checked Redstone, which is the next version of Windows 10, but hopefully it's something. So a few references, the sandbox analysis tools, symbolic link tools. Also, like, in my opinion, while it's quite complicated, the Chrome sandbox code is open source. You can look at that, how we actually implement Win30k lockdown, how we actually implement those sort of features. So give it a look. So that's the end of my talk. Obviously, if anyone's got any questions, I will be around, obviously. the rest of the day, so you don't have to do it now, but thanks very much.
Other questions? Are there questions?
Cool.
Doesn't look like. So, James,
Awesome.
again, thank you very much.
Thank you.